Okay, so here we are in the lab again. And so this is episode 5 of Build Your Own Main Brain Microcontroller Project. So, uh, speaking of main brain, it's right here. I have main brain working and it is communicating with the motion board, and the motion board is controlling the speed and the direction of the motor, which right now means it's running. But it will. There will be sequences of motion that you can build and send to the microcontroller, and then it'll execute those sequences like accelerate, run for a certain amount of time at a certain speed, and decelerate, and all that stuff. And you can make it go back and forth like a washing machine if you wanted to, or whatever. My what I plan to do with it is to build a robot. So I'm excited that I finally got the front end revisioned into the motion board, and it's all working good and ready to go. And so that's one of the things that you one of the many things that you can do with MainBrain. All right. So uh, we went over the configuration bits last time, and but we just got the first block done. So that's where we wrapped it up because we were hitting the 30-minute mark. And so this video, we're going to finish the configuration bits, and then we can get moving on to something else, because I'm sure configuration bits isn't everybody's favorite thing to do. But you got to know it, because that's what makes your microcontroller do whatever you want it to do. And so it's important we know about this stuff. So we'll even get into it deeper later, because we're just skimming over the top right now to get through it. So we just want to know, we just want to get our minds around what they are and what they can do and what options we have later on down the road. So, and that's like I said in the last video, when the microcontroller powers up, the very first thing it does is to load those configuration bits before it does anything. So let's get on to it. Okay, so device configuration register number 2 is basically for the clock setup for the core. Well, the master clock for that is for eventually becomes for everything. So let's jump over here real quick. And this is the diagram for the clock. So this is our primary oscillator. So you can use a crystal, or you can use an external oscillator, which I do. I have better luck that way, because these caps and the capacitance and resistance in just the traces make it difficult to get a good signal, especially when you're changing stuff in development. So I just use an oscillator. It's about the same cost anyway. And then with an oscillator, you just use the one pin for this the clock coming in, and then this one, in some circumstances, you can use it as an output, a divide by 2 clock, a divide by 2 of this coming out, but not in all modes. So you can see that it comes in and it goes off to the system, but it also comes up here and it goes to the USB, and that says you can only have a 12 or 24 megahertz clock here. The CPU will run on any frequency up to like 65, so 60 something megahertz, but you need to have 12 or 24 if you're going to use USB, which I do on my board. So I use a 24 megahertz oscillator. So it comes in and it comes up here. Now you can switch. You can use the internal FRC oscillator, which is 8 megahertz. So it can come in and you can switch which one you want. And this PLLI clock is over here, and that's this one here, PLLI clock. And so we have it set right here for the PLLP oscillator and not the FRC. Okay. So then it comes in, and it has to be, when it comes in here, it has to be at 8 megahertz approximately. So you use this divide by N PLLI division register here, and that is PLLI division right here. So we divide it by 3. So you got a 24 megahertz coming in, divided by 3, that's your 8. So you set the range here with this FPLL range register. So our range is from 5 to 10 megahertz because it's 8. All right. So then come over back over here. So it comes in, it hits the PLL. So the PLL has a note, and you come down here to 6. Oh, it tells you. Never mind. All right, so it comes through the PLL, and you multiply it to get a certain frequency. All right, and so this is PLL multiplier. So this is PLL multiplier. So I have mine at 50. So you're at 8 megahertz times 50, and that's 400 megahertz, right? All right, so then it comes over here, and this is the PLL out division, divide by N. And so you want to set that to a certain frequency for your system. And so that's PLL out divisor, which is 2. So that sets us at our 200 megahertz. So when this one boots up, we're at 200 megahertz system clock. Okay. Okay, so that was device configuration register number 2. So that was primarily the clock oscillators configuration block. So now we'll go on to the next one. Okay, device configuration register number 1. So the first one on the list is FNOSC. That determines which oscillator is used right when the device starts up after a reset or gets powered on. Before it starts loading any firmware, this is the oscillator that will be used. So I use the SPLL, which is the one that we set up in the last one. So, but it does a switch over. You can do a 2-stage clock or a dual startup clock to where you can start up on one clock and you can switch to the other. And usually you would start to a lower frequency and go up to a higher frequency. But there's several options available, and we'll cover all the options in the oscillator video. All right. Okay, so DMTINTB, that is the watchdog timer interval. So for those of you who don't know what a watchdog timer is, it runs independently of the of your program, and so if it doesn't, it has to get reset within its window. Okay, so we have available from 2.5 milliseconds to I think 36 seconds or something like that. So you can set it a whole bunch of different windows, they call it, and so it runs continuously. And if your program hangs, then it detects that, because your program will have to periodically reset the timer, because if you let the timer expire, it resets the system. So that's why they call it a dead watchdog timer. It's like if your program locks, and if it didn't have a watchdog timer, it would just sit there and just stay locked for however long until somebody discovers it. But with the watchdog timer, since the program is locked, it can't reset the timer. So the timer resets the microcontroller, and hopefully, whatever caused the software to lock up uh, or stop running is cleared, and it can continue on in normal operation. If not, then it'll just keep the watchdog will just keep resetting after whatever time it has set in this range up here. All right, and so we'll go over that too later in more detail. All right, so then the next one is this FSOSCEN. So when it's an EN, it's going to be an enable. And that means it is for the secondary oscillator. That's primarily used for a real-time clock. So if you don't have a secondary oscillator of 32 kilohertz, actually 32.768 is for a real-time clock. And if you don't have one, then this must be disabled, probably because the input would be floating or something, and it might cause it to oscillate. I'm not sure, but they say you shouldn't enable it if there's no oscillator on there. I do use the oscillator for a real-time clock on mainbrain. So this enables it at right after reset when the system starts up. Okay, so the IESO is the uh, enable for the 2-speed startup. So the idea is if you need to start up like really fast, then you can use the FRC as the startup clock and then switch over later once the PLL, and because it takes a few milliseconds for the PLL and the primary oscillator to stabilize on startup before it's actually ready where the PLL locks and it's ready to generate a clock. So it's important in your code to make sure those are stable before you start loading code and stuff. So, but you can do a single startup or you can do a dual startup. Okay, then POSCMOD, that determines how the clock is going to be configured at the pins, oscillator pin 1 and oscillator pin 2. So EC here is external, and you can do it so that you don't use the external oscillator, and you can you have to set it. If you use a crystal, you have to set it for that XT mode or HS mode, or you can disable it and use the pins for IO. Okay, then we have POSCMOD. That is the way that we configure the primary oscillator pins. Oscillator 1 and pin oscillator 2. And so you have 3 choices. You can have an external one, which is EC. So when you use like an external oscillator or some external signal, it doesn't have to be an oscillator. It can be any kind of clock signal that goes in that meets this frequency requirement. Or you can set it for high speed for a crystal, or XT for a crystal, which I believe is low power. We'll touch on that in the oscillator video. And then we have the OSCIOFNC bit, and so it determines what the configuration for the oscillator 2 pin. So in some instances, it can be configured as the oscillator out, and it's also used for the crystals to complete the crystal circuit because you need 2 pins for that. And so when it is on, then it is set for digital I/O. And when it is off, it outputs the primary oscillator frequency in not all circumstances. And we'll have to get into that too in the oscillator video. And then we have FCKSM. That is for clock switching enabling and also clock monitoring. So if your primary oscillator fails, it can be set to reset, and that can be turned on and off, as well as clock switching can be enabled, or you can disable clock switching. And then we have the WDTPS, which is for the watchdog timer. That is how you set the time. So it can go from 500 nanoseconds approximately up to 32 seconds by the number. So 1-to-1, it's a post scale divider. So the number determines the division of the clock of the watchdog timer. And then we have WDTSPGM. This is to disable the watchdog timer while you're updating the firmware or programming the device. You can turn that off, or you can leave it on, and if some reason you need it while programming or something like that. Next up, we have FWDTEN. So that enables or disables the watchdog timer during startup and allows you to turn it on and off in software or to have it start running at startup. And then we have WINDIS, which is a enable, disable for the watchdog timer windowed mode. So you can have 2 ways to reset the watchdog timer. You have 2 choices. You can just let the watchdog timer run, and any time that you reset it before it times out, then it resets the watchdog. Or you can have windowed mode where you can only reset the watchdog timer in a specific range or a window. So when this is on, the watchdog timer runs in windowed mode. When this bit is off, it runs in normal mode. Okay, this is a long one. It is FWDTWINSZ. This sets the size of the window for the watchdog timer if the window mode is enabled. You have 3 choices. You have 25%, 50%, or 75% of the setting of WDTPS above. And next we have DMTCNT, which is the dead man timer, which is just like the watchdog timer, except it acts on the CPU. So if the CPU locks up, then this will reset it. And then last but not least, we have FDMTEN. EN is an enable. So that is an enable for the dead man timer. So if you don't want to use the dead man timer, you turn this off. If you want to use it, you turn this bit on. Okay, so now we got one more block to do and then we'll be done. This was going to be a long one, but then we'll be done with the configuration bits and then we can move on to some other stuff. Okay, here we are at device configuration register 0. Okay, so debug. This enables or disables debug for when you use the ICD or what they have a real ICE platform that you can use, or JTAG. So as long as this is enabled, then you can access it with those features. If it's off, then after It's like for a board in production, you can't go in and try to get into the code and change it, read it, or anything like that. All right, and the next one is the JTAG enable. So he just turns JTAG ability on or off, which is a debugging thing called boundary scan. We might get into that. I don't know. It's not on the top of the list, but it could get there. It's important in engineering and stuff like that if you want to learn about that. Next, we have the ICE-SEL. That is there's two sets of pins for the in-circuit emulation and debugging. So you can use, depending on which I/O pins you need, you can switch between ICS1 or ICS2 pins. But if you're not going to do any in-circuit debugging or anything like that, then you don't have to worry about it. Okay, and then TRCEN is trace enable. That's for advanced debugging where you can see the instructions and code and stuff like that in real time. And it's if you have the advanced debugging tools, that would be what you would use. You would enable that. Okay, and then this boot ISA is for the core, the MK4 or the M4K core. So it can boot up in the MIPS standard MIPS 32, or it can use a more compressed form of 16-bit, 32/16-bit compressed code called mini MIPS, and that's to make smaller compact code. So sometimes embedded systems need really small code. And FECCCON is the error correction code. You can do 1-bit, 2-bit, stuff like that on the program flash memory. And we'll get into that when we cover the flash memory. All right. And this F-sleep is when it's off, the I/O pins act normally. When it goes into sleep, they retain their values. But if this is on, when it goes into sleep mode, then it puts all the I/O pins in high impedance state to save on energy consumption. And then we have DBGPER. That's for debug mode. You can have all the peripherals on, you can have all the peripherals off, or you can have a certain, like half of the peripherals on or off. All right. And we'll cover that too because we have to cover sleep mode for power savings, just like your cell phone dims the screen or turns the screen off, stuff like that. Yeah, we're going to cover some of that too. So this next one, SMCLR, has to do with the master clear pin where we do our reset. And so if you need more I/O, you can actually disable this pin and rely on software, the firmware to reset the microcontroller. Kind of scary if you ask me, but you can do it. This is in normal mode because we use the reset supervisor and stuff like that on mainbrain. So then we have the SOS C gain, which is the secondary oscillator gain. You can turn the gain up or down for the secondary oscillator. This is mostly applicable for if you use a crystal for the oscillator. And this next one, the SOSCB boost, that is for a crystal oscillator as well to boost the drive of it while it's being powered up to help with the better startup with the or with the crystal. And then P-os gain is the primary oscillator gain. You can do the same thing with the primary oscillator as the secondary oscillator. So you can provide gain if you're using a crystal instead of an oscillator. And then the next one is this boost for the primary oscillator. Same, you can boost it the same way you can boost the secondary oscillator if you are using a crystal. This is not needed when you have a external oscillator. And this EJTAGBEN is for an enhanced JTAG enable or disable. And that's for JTAG debugging of the MIPS core. And finally, last but definitely not least, is CP, which is code protection. If it's turned on, then you are not able to access the code externally in any way, whether you have a programmer, debugger, or anything else. It is not accessible. It can be executed, but it cannot be read. So when you're developing, you definitely want this thing off. And once this is turned on, you have to erase the chip completely before you can program it again. So once again, we leave CP off until we are ready to send it to the real world. Okay, there you go. Wow, this is a long one. So there's the configuration bits that gets the processor going so that you can do whatever you need to do with it and set the speed and all that good stuff. And it's primarily for the oscillator setup. And so we'll be covering the oscillator maybe next. I don't know. I'll have to look. But yeah, we got the configuration bits behind us. Okay. So I will see you in the next video.